1.8 is valence electrons and ions, and the outcome is I can explain the relationship between trends in the reactivity of elements and periodicity. So what I want you to do first is to generate several graphs here. This is going to show the atomic number versus the melting points. So let's look at how to make one of these graphs. So here I have an Excel spreadsheet, and what I've done is I've just collected my data from the website and I organized it into columns. Now an important thing to know in Excel is that that first column that you select for your graph will be your X. So I want my X-axis to be atomic number. So I'm just going to click and drag and select those cells. Now I want to select my Y values, my vertical axis. So I'm going to press Control and then click on melting point and click and drag to select those. So now I'm going to go to Insert and I'm going to choose a scatter plot. I'm just going to choose the one that has smooth lines. And then this is the graph that we end up with here. So I like to do just a little bit of cleanup here. I like to put axes on here. So this axis is the melting point, which is in Kelvin. And then this axis here is the atomic number. And then just so we know which graph this is, I'm going to call this Group 1 metals. Okay, so I'm going to produce all of these graphs in a similar fashion, going ahead and collecting the data and then highlighting my columns and then inserting the graph and putting in all of these little details. So in general, the weaker attraction between valence electrons and the nucleus means a lower melting point. So in metals, each atom gives up electrons. It forms an ion, forms a cation, and then those electrons get shared in the electron sea. So the more attracted the electron sea is to its cations, the harder it's going to be to break apart those attractions and the higher the melting point will be. So for these graphs, we see that in our group 1 metals that the melting point is decreasing, and that's because those valence electrons are farther away from the nucleus, so the attraction is weaker. As we move across period 3, we see a general increase in the trends. When we have something that breaks the trends, it's almost always something in the transition metals block. But here we see a similar relationship where as we go across the row, the attraction is stronger. That makes sense because the core charge of the nucleus is increasing. Now when we look at our period 4 and our period 5 metals, we see that there's a trend where we're increasing, and then we dip down. And for period 4 metals, that occurs at atomic number 25, which is Mn. And if we look at period 5 metals, we have a similar dip here that corresponds to Tc, which is underneath Mn. So there must be something about the attractive forces that are a little bit weaker there. It could be the arrangement of the electrons. There's more electron-electron repulsion. Something like that could cause that. And then in period 6, I skipped the lanthanide series, so I just included the main group elements, but we see a similar trend here where increasing, and then decreasing. So again, this is because the attraction in that nucleus must be changing as we go across and add more protons. So next I wanted you to observe the reaction whenever alkali metals are exposed to air. And one of the things they say in the video is that this gradually becomes more terrifying as we go down the group. So alkali metals become more reactive as you go down a column. So metals react by losing electrons to form cations. So explain the trend in the reactivity of alkali metals. So as we go down the column, down the group, the valence electron is further and further from the nucleus, so it's easier to lose it. So metals like cesium and francium very easily and readily lose that valence electron, meaning that they react more vigorously. For your reflection questions, we know that group 2 metals form chloride salts in the form of XCl2. How can we confirm this ratio, and how does this support our understanding of the electronic structure? So we can confirm those ratios using percent by mass. If we take this magnesium chloride salt and we do its percent by mass, we can figure out that there's twice as many atoms of chlorine as there are magnesium. So we can support that ratio using information from mass spec. How does this finding support our understanding of electronic structure? So those group 2 metals are all going to lose 2 electrons and form cations. So this is because they have 2 electrons in their valence shell. And chlorine, we know, needs to gain a valence electron. So the fact that they react in this ratio supports that I need 1 magnesium to 2 chlorines because of the valence electrons.